Recording. Uh, this is arc welding. Last time we were talking about the arc welding, consumable electrode, consumable electrode. Arc welding, as I told you last time, arc welding is we have consumable electrode and non-consumable electrode. Consumable electrode, if we start with the consumable electrode, there are a shelled metal arc welding, gas metal arc welding, flux cored arc welding, electro gas, and submerged arc welding. This is the welding type that we're going to cover under consumable arc welding, and then go to non-consumable arc welding, right? Also, just to remind you, we were talking about consumable arc welding. This is a shielded metal arc welding. Shielded metal arc welding يعني it means that we said metal, the word metal, to remind you that what we discussed last time, the word metal is related to the core, related to the core, this one. The core of this metal here related to the core. Metal mean metal compatible, a core made of metal compatible with the workpiece material. If you welding steel, it will steel, welding copper, copper, welding aluminium, aluminium, and so on. Shielded metal, and shielded here by using flux coated with a flux here, so shielded metal arc welding. That's what we discussed last time, and also we discussed about the process. Shielded metal arc welding, this is a shielded metal arc welding process. Also we discussed last time about the straight polarity, reverse polarity, just to remind you what we discussed last time. And then we discussed also submerged arc welding. And submerged arc welding, as I told you also, it is a continuous welding process. Wire here is obtained from a spool, very long wires, and continuous. It's like continuous arc welding process. This is a wire, consumable wire, and here the flux is provided as a powder. We call it is submerged arc welding because welding done below. This is the next, which is horizontal. This one limited to horizontal welding process. Next, we have improvement, which is a gas metal. Word metal here indicating this consumable arc welding. Metal here meaning this kind of wire. This wire, continuous wire electrode, continuous wire electrode is metal. Metal mean consumable arc welding. And here we shielding by gas. This is inert gas. We shielding by inert gas. Shielding mean protect the weld by using inert gas. We call it MEG, metal inert gas, mean inert gas or gas metal arc welding, GMAW. This also we discussed last time. And finally, we discussed about the flux core arc welding. And I told you that time flux core meaning the flux, we put the flux in the core, not coating, but in the core. Then when the filler, this is a filler material, and this is the core flux. When the filler is melted, this one is evaporated. I mean, the flux will be evaporated, creating the needed gas to protect, and definitely slag will be created and so on. But here this one made in a core to protect the flux itself, so functionalize better than the flux when it coated with gas or shielded metal arc welding process. That's what we discussed, and we stop here last time. Electro slag welding process, we stop here last time. Electro slag welding process, right? Okay, so right. Okay, electroslag working process. They call it electroslag welding process. In electroslag welding process, we welding vertical edges. This is one edge, this is another edge. Can you see that? This is one edge, this is another edge. We would like to weld this vertical edges. There's two vertical edges here, this one and that one, and the weld here in the middle, as you can see. This is the method, we call it is electroslag method or welding method. Let me show you first video and then just come to explain the feature of electroslag process. Okay. Okay, this is a video. This is the two walls that we would like to weld now. These two walls or two edges. This is the metal one. This is metal two. Then electroslag welding process. This is a packing plate. We put plate here as a packing plate. This is a shoe, copper shoe. This is one and another two copper shoe. This one to prevent the melted material or welded material to spill out. Put here this is the flux hopper. We put flux. We fill this gap between the two shoes with the flux. This is a continuous wire. This is a wire. We bring the wire here. Then continuous feeding wire. So this is a wire. We bring wire down. This is a wire as you can see here. This is the flux. You switch on. When you switch on, electrical arc discharge will happen here. The discharge will happen here. Electrical arc will be created. The wire will be melted. Wire will be melted. This wire will be melted and deposited as filler, and also flux will be evaporated and create enough gases to prevent, and also slag will be created and float up and become creating a layer at the top of the weld. So this is a process. This is slag, molten slag. And then this is shoe. There are we circulating water inside the shoe. We're circulating water to absorb heat quickly, solidify. Then again, one more time. This is here you apply electricity. Arc will be created. This one will be melted and deposited. Flux also will be evaporated, creating gas, and react with the slag. React as a slag, react and create slag. Slag will flow up and create, this is a layer, this slag layer, if you can realize. Right. Here, this is the shoe. The shoe here is made of copper usually. We're circulating water inside. Circulating water inside. The water here mainly to absorb the heat, to quickly solidify, and then shoe will moving up as you can see, moving up, then this one solidify and moving up, and you get all done. So well done. So now we weld this two material vertically. We weld this two material as you can see here. Okay, get back to the slide again. So this is, as I told you, is electro slag welding process. Electro slag welding process. In electro slag welding process, as you can see, we're welding two vertical walls. This is vertical wall and two vertical wall. Welding two vertical walls, as you can see. This is the shoe. This is the one shoe. It is made of copper. We're circulating water here, as you can see. This is the input and output. We bring water here as an output from here. The water, the main idea, water here absorb heat here to solidify quickly. Yeah, guys, yeah. Time now is finished. I'm going to continue the class. If you would like to stay, you are very welcome. If you don't want to stay, then you can just simply now, you can just go. No problem. I will continue the class, and then this one will be recorded in the Blackboard. If you would like to go, if you have anything now, if you're busy, I understand you can go. If you would like to stay, you are very welcome. Right.
Thanks a lot.
Okay, guys. Yeah, sure, no problem. So this is, as I told you, this is the shoe. It's made of copper, and we circulating water inside to cool it quickly, absorb heat here and cool it quickly, then solidify. This is a wire, maybe more than one wire, not necessarily one wire, maybe more than, here you can see that, more than one wire be used, then because probably the area. Very welcome, Muhammad. You are very welcome, everybody.
Dr.
Right,
Ahmed,
so we have one. Yes.
before I leave, Doctor, what about can you بس fund do for the homework.
Homework, I'm sorry, because you know that Muhammad homework is not only me. This is a coordinating subject, and I mean, not all of us. I mean, in a meeting, we made meeting before and decided to not postpone any homework. I'm sorry for that. It is not really out.
It's
It's totally out of my hand.
mid time, Doctor. No.
Sorry, cannot. I'm sorry. Decided not to postpone any homework. The one I have in my hand, I can do. But this one, because it is coordinating subject, it is difficult to change. I'm sorry. It must be submitted on time. Sorry,
But also, we
accept
have a
my.
mid before the day before and a mid in the same day. So
I understand. I understand. Yeah. Anyway, so yeah, please accept my apologize for this one. Again, get back here. This is a copper with circulating water to cool it down. You get solid. You put four wire here to deposit a big amount of material, maybe bigger place, maybe the area is big, small. So it depends actually. So you can add it more than. Then you get the well done between the vertical wall. This is whatever we call is they call it electroslag because slag here is created. They call it electroslag because slag here is created, as you can see, in the weld. Right. This is a discussion explanation about this one. Thickness range from 50 to 900 millimeter actually could be done. And this is the details actually of the electroslag welding process. Another process we call electrogas. Not slag but gas. It is very similar to what we had before. It's also consumable electrode. Still, we talk about consumable electrode, continuous consumable electrode. The wire also we use a wire. Wire is continuously delivered from spool here. The difference between electro gas and electro slag is that we are not using here flux. We use a little flux, but mainly gas. We shielding by gas. We shielding by gas. We pumping gas. This is pumping gas from here. So gas, what gas? Inert gas. We shielding by using inert gas. That's why they call it electro gas. This is a wire. Wire will be melted and deposited. Wire will be melted and deposited, as you can see here. This is the shoe. Same. This is the circulating water. Also same. But here we're pumping gas. Instead of the flux, we're pumping gas and the gas will shield here. So shield will be done by using gas. So you call it electrogas welding process. This is a consumable electrode, and here there are a comparison between electrogas and electroslag welding process. This is about the consumable electrode. Next is the non-consumable electrode. Non-consumable electrode, you expect what? You expect that electrode will not be melted. Electrode will not be melted and will not be deposited. Why? Because electrode made of materials that have very high melting temperature like tungsten, always tungsten. Non-consumable electrode usually made of tungsten. So this is a non-consumable electrode. This is a non-consumable electrode. Non-consumable made of tungsten. They call it is a gas tungsten arc welding. Word tungsten here related to the electrode. So gas tungsten arc welding. Gas tungsten arc welding. So electrode made of tungsten. So gas tungsten. If you find here the gas tungsten, then it is non-consumable electrode. So GTAW, gas tungsten arc welding. In this case, filler must be added, as you can see here, separately. Filler must be added here separately, and we shielding by gas. So we pumping gas here. This is inert gas. Pumping here inert gas to shield the weld, and filler added, as you can see here, separately. So in this case, gas tungsten arc welding or non-consumable electrode, same electrode being used for welding wide range of material because it is not melted and deposited in a weld. zone. So we can use same electrode to weld several type of material. Filler is a material must be compatible with the base material, right? To wide variety of application and metal can be used for aluminium, magnesium, titanium as a fractal metal suitable for thin metal. AC and DC can be applied, and then this one shelled by, as you can see here, shelled by gas. Sometimes you call it TIG. TIG means tungsten inert gas. They call it is gas tungsten arc welding or TIG. TIG meaning tungsten inert gas welding process. Next is the plasma arc welding. Plasma arc welding. So here we creating plasma. Plasma, this is the plasma. Oh, temperature is very high. Produced from the plasma temperature is very high. Actually, in the plasma, we pumping actually the word plasma. What is the plasma? First, what is the plasma? Plasma is, listen to me carefully, please. Plasma is ionized superheated gas. Plasma mean ionized superheated gas. So we use a gas here. So there what we call is a plasma gas. If you realize here, you find different here. We're pumping here. This is the inner gas to shell in the outer ring. We put or we're pumping inert gas to shell, and in inner ring here we pumping plasma gas. There are two types of gas here. This outer one is inert gas to shell. The inner one we pumping plasma gas. There are a gas we pump here we consider is the plasma gas. Electrode is tungsten. Electrode is made of tungsten. Electrode made of tungsten, exactly same as the non, because it is non-consumable electrode. Let me explain about that. In a plasma arc welding, you can see that we're pumping, as I told you, two type of gas. The outer here is a shielding gas. This is a shielding gas to shield, inert gas to shield. The inner here, the gas we pump here is a plasma gas. We call it the plasma gas. What happening and how ionized superheated gas produced? Actually, Actually, this is really important. I hope you give me your attention. This is the electrode. This is a filament electrode made of tungsten. Why tungsten? High melting temperature material. It is non-consumable electrode. This is a workpiece. First, you connect power between, or you initiate the power between the electrode and workpiece. The potential difference increase whenever you switch on the power. Potential difference between electrode and workpiece increase. It's kind up to 150 kilovolt. Then when you reach up to certain limit, electron jump, as you can see here. Electron jump from electrode to the workpiece. Then this is the electron, the beam of electron between electrode and workpiece. Yeah, however, we're pumping here gas. This is a plasma gas. We're pumping here a plasma gas. So plasma gas here cut the stream of the electrons. Plasma gas here cut the stream of the electrons. So plasma gas absorbs the energy of the electron. Electron is very small, but having uh, uh, energy. The energy of the electron absorbed by the gas, because electron this gas will resist and prevent electron from reaching to workpiece. This gas in a way will stop the electron and absorb the kinetic energy from electrons, and this energy absorbed in a gas will ionize the gas. The energy absorbed by the gas will ionize the gas. For example, if you're pumping a nitrogen, then N2 plus energy become 2N. 2N, N2 is connected, 2N is separated, as you can see. And then more energy, 2N get more energy, then lose the free electron in the last orbital and become ion. Then become ion, nitrogen become ions, as you can see, plus free electrons. In this case, nitrogen is unstable, would like to get back again to the stable condition. This is a stable condition. N2 would like to get back again to the stable condition, which is N2. So once nitrogen exit from this area, then immediately nitrogen recombined nitrogen become N2 plus energy. Nitrogen change. What happened is nitrogen change, nitrogen again, absorb electron, nitrogen absorb electron from the environment and then recombined become 2N, 2N become N2 and release energy. This energy is very high, heat. Then whatever energy absorbed here is released here as a matter of heat. Then heat increase here up to a high, very high temperature. We call it is this is ionized superheated gas. That's why we call ionized superheated gas, because the gas here ionized. So we call it ionized superheated gas. And this temperature can melt, and here a welding could be done. So we melt the base material, substrate material, and weld could be done. This is whatever we call is a plasma. So plasma created based on the ionized superheated gas. There are two methods of plasma welding. There we call it transfer and non-transfer. The big difference between transferred and non-transferred, here we connect electricity between electrode and workpiece. However, here we connect electricity between electrode and the body of the nozzle, plasma nozzle. We connect with the body of the plasma nozzle. So what is the big difference? Actually, here, if you connect with the workpiece is better. This one leading to many problems, because when you connect with the nozzle, mainly you can see that electron beam temperature will be very high here at this area. Temperature will be accumulated very high here. This one damages the nozzle, and you need to change the nozzle frequently actually. However, this one better, because this one temperature will be accumulated here in a workpiece. And this one is better because this one help a more professional and more performance is better in welding material. However, in this case, when you connect filament and workpiece, then workpiece must be conductive material. You must weld only, is limited only if you connect filament with the workpiece, meaning you must or you can only limited this welding process limited to the conducted material workpiece as a conducted. Transferred method limited to conducted workpiece. If the workpiece non-conducted material, this one cannot be work. It must be. However, in this case, even with this kind of a disadvantage that damage the nozzle and frequently change and so on. However, this solves the problem of the conducted material. Here, in non-transfer method, we can weld either conducted material or non-electrical conducted material. This is the big difference between transferred and non-transferred method in the plasma arc welding. Right. Next is carbon arc welding. Another method is the carbon arc welding. Carbon arc welding use here the electrode made of graphite, non-consumable graphite. It is electrode here. It is now currently tungsten. This is the old one, and currently is not being used since tungsten is introduced. This one not commonly used. However, it is still exists in an industry with electrode, non-consumable electrode made of graphite, and this one is still being used. Only the difference is this one made of graphite. And shielding by gas also, shielding by gas here. And this is the old method actually, and being used in brazing and preparing iron casting, depositing some wear resistance material and so on. But when tungsten introduced, this method is not commonly used now. However, it is still exists in the industry. Next is non-consumable electrode is a stud welding. This what we call is a stud welding. Actually, the idea, this is a stud welding process. The idea is to weld this stud with the workpiece. So finally get this joint. We need to get this joint at the end of the process. So this one is the stud and electrode at the same time. We connect electricity between the stud and workpiece. This we call it stud arc weld. Stud and workpiece. We connect the electricity here, and then when this one we use ceramic ferrule. This one ceramic ferrule is only to use for positioning stud in a correct place, positioning stud in a correct place, and also used to prevent or to isolate this area from the air, from the environment in somehow. Then initially you check the position, you fix the stud in a correct position with the workpiece. Second, you connect also electricity between stud and workpiece. Second, stud, you move the stud, and separate here, get gap, move a little bit, move the stud to get a gap, enough gap, and then arc will be created. This is the discharge happen. Discharge happen between the stud, and this is the electron jump as the arc will be created. When the arc is created, this is the discharge, mean electrical energy change to thermal energy, and then temperature increase. This one will be melted, this one will be melted. Then you get liquid pool here, and then you move the stud again inside the molten pool. Then stud will be positioned in the stud plug into the molten pool. Here, as you can see, you leave for a while solidification, you remove the ferrule, and then you get the weld done. This whatever we call stud welding for certain case, for very special cases, to create or to find or to obtain this kind of joint in a welding. Next is we're going to talk about resistance welding. So previously we were talking about arc welding, consumable electrode and non-consumable, or arc welding, consumable electrode and non-consumable electrode. Now we're going to talk about another type of welding, which is the resistance welding. I believe we discussed this one also last time. This is the resistance welding. And here there are a big resistance. This is the resistance area between these two parts. This is an example. This is a spot welding. We discussed that previously. I hope you remember that. This is the one electrode. This is the second electrode, probably copper electrode. We connect the electricity here. We're pushing big amount of current. We're pushing big amount of current from this electrode to this electrode. So current would like to move. However, here in a contact area, let me highlight here in the contact area between the two plates, exactly in the middle, here is a contact area between the two. You can find that these two plates here connected in a few points, and the current would like the big amount of current that you push here would like to move through this few points. They get traffic jam here, you get big loss of energy, and then we call it high resistance. That's why we call it resistance welding, because current cannot easily go from up to down, this kind of resistance. Then here the resistance point, big loss of energy, you get energy waste, and this energy waste lead to temperature increase. You get melt, this area will be melted, weld will be done here between this one. This is a spot welding as a case, then the weld will done in exactly in this spot between the two electrodes. This one electrode, this is another electrode, well done here in this, exactly in this area. This call it resistance. This is the fundamental of resistance welding. In resistance welding, generally, if you say the resistance welding, generally, here no flux. Resistance welding, there are no flux being, we cannot smelt, now we melt. It's vision welding. Vision welding and no flux. Vision welding and no flux, we can consider it as an autogeneous weld. So this one we consider it as an autogeneous because no flux being added, even it is, because very difficult how to put the flux in this area. No flux being used, no filler also being used, right? Heat generated is here, the area here, weld area. This is the electrode, this is another electrode, and then this whatever we call weld nuggets. We call it like this, weld nuggets. The weld nuggets is a weld area. The weld zone, we call it weld nuggets, like this, similar to, this is the shape of the weld nuggets happening here, between these two parts. Then not up, not down, in the middle. Weld will happen in the middle. This is the shape of the, usually, this is the shape of the weld nuggets, actually. Right. Then a heat equal to I square RT, heat in joule, equal to I square current, R resistance, multiplied by the time of the weld. And this time of the weld, let me tell you, it is a fraction of second. Fraction of second mean less than a second, fraction of second. Then you get heat in joule. You get heat in joule. In this case, if you have a heat, this is the heat at the source. Heat at the source, H equal to I square RT in joule. In this case, use HW in weld. This is the heat in weld equal to F1 multiplied by F2 multiplied by H. This is the H as a source, which is equal to I square RT equal to UMV. This is the one equation. If you multiply I square R only, no T here, I square R only, I square R equal to joule per second, which is the heat rate, which is RH as a source. In this case, you can use the second equation, RHW equal to F1, F2, RH. The big difference between the first case and second case, in the first case, this is the heat. If you multiply by T, this 1 second case joule per second. If you multiply by T, which is second, then second goes second, you get joule. So here is the heat in joule. This is the heat rate in joule per second. So you can either have this case or this case. Then you have to understand, actually. You have to understand whether what is the case to deal with. If you have the power case or a heat rate case, then you use this equation. If you have only heat or joule, then you have to use this kind of equation. Right, let's take an example and let's understand and solve together. A resistance spot welding. Okay, this is an example. A resistance spot welding, this one, resistance spot welding, this one, operation is performed in two pieces of 1.5 millimeter thickness. This is the one piece, work piece. This another one, 1.5 and 1.5. This is the thickness of the two work piece. Steel using, this is a steel made of steel using 12,000 ampere. Current here, current being used here is 12,000 ampere. Let me highlight. Current is 12,000 ampere and duration is 0.2 second. This is the time. The weld done very fast. The weld done here in 0.2 second, very short time. Electrode, this electrode 6 millimeter in diameter. Usually the diameter of the electrode is exactly same diameter of the weld nuggets, or the weld nuggets will be created exactly matching with the diameter of the electrode. So if the diameter electrode 6 millimeter, then you get diameter of the weld nuggets will be 6 millimeter. Anyway, just to let you know, so the electrode area usually, the electrode area is 6 millimeter in diameter. Electrode diameter is 6 millimeter in diameter at contact surface. This exactly, so electrode diameter in a contact surface, this is very important, is matching with this one. Resistance is given. This is the resistance. Resistance between, this is 0.0001 ohm. This is the resistance in between. Resistance here in the middle. Exactly resistance between the two plates is given. And the result, weld nugget 6 millimeter in diameter. So weld nuggets here is 6 millimeter in diameter and 2.5 millimeter thickness. Thickness here is 2.5 millimeter. 6 millimeter diameter, 2.5 millimeter thickness. Unit melt is given. Unit melt for this material is given. what portion of heat generated was used to form the weld nuggets? How many percent will be used to produce the weld nuggets of the heat generated? The heat generated at the source. The heat generated at the source. This is the heat generated at the source equal to I square RT. I square RT heat generated at the source, right? Equal to I square is given, R given, and T given. Then you apply, you get joule. This is the heat generated. This is the heat generated at the source, right? Heat generated at the source. Okay, right. This is the heat generated at the source, right? I don't have F1 and FT. I didn't give F1. The question is what portion of heat generated at the weld. The question is what is the F1 and F2? What is the F1 and F2 in this case? Actually, we can calculate the volume of the weld nuggets. The volume of the weld nuggets here is 2.5 millimeter thickness, 6 millimeter diameter. It is by R square or by D square divided by 4 multiplied by thickness. Then you get the volume of the weld nugget. UM is given. UMV give HW. Then we know HW now. Then HW is here. So HW equal to UMV. UM is given here and V is given, or we calculate V and UM is or also known. Then we can just get HW. Then HW equal to 848. This is the HW, which is the heat needed, heat required to do the weld. This is the heat required to do the weld, which is HW. This is the heat generated as a source. The difference will be waste. The difference between heat generated as a source and heat needed for the weld is the waste. So 2000, this is the 2080. This is the 2880, the heat generated at the source. And this is the 848 joule, which is heat needed for the weld. The difference, the balance is this one. 70% of the heat will be lost. 70% of the heat is lost actually in here and in here. Then this is this one definitely related to F1 and F2. This amount of heat loss is related to F1 and F2. Something else, if you get just only I square R, if you have I square R, then you get joule per second. If you multiply only I square R, if you multiply I square RT, you get joule. If you multiply I square R, you get joule per second. Joule per second is, you can apply to get also joule per second. So this is, be careful about that. This is I square RT meaning heat, I square R meaning joule per second or heat rate. Right. This is a question. In the resistance welding, not only spot welding, but also we have seam welding and we have whatever we call projection welding. So we have a spot welding, seam welding, and projection welding. Let us show together. Spot welding that we know already, we discussed that before. This is a spot welding. In a spot welding, we have two electrodes. This is upper electrode, this is a lower electrode. We apply little pressure for positioning here. We push big amount of current, and this is the resistance. Then you get the spot weld here. This is the weld nuggets. This is the weld nuggets. Usually the diameter of the electrode as the contact area is equal to the diameter of the weld nugget. Weld nuggets will be created. This is a spot weld, and the weld done exactly at certain spot where electrode is positioning, right? Next is this is a machine. You can see this is a spot welding machine. This is a two electrode. This is different model and different design. This is the two parts that you would like to weld. This is electrode, upper electrode and lower electrode. Usually electrode made of copper. This electrode made of copper. Why copper? Because copper have very good electrical and thermal conductivity. Electrical conductivity because mainly here we need to push big amount of current. So we need to have electrode made of material have very good electrical conductivity, right? This is one. Also the other benefits is this electrode have made of copper have very good thermal conductivity. When you have very good thermal conductivity, it help actually. It help to do, you can just make a cooling system around to absorb heat quickly from this one, so you can protect electrode from the damage because it is very good in thermal conductivity. Other material is a copper tungsten. Copper tungsten, we added here tungsten to the copper, not only copper, but we added tungsten. When you added tungsten to the copper to increase the melting temperature, because tungsten very high melting temperature material. When you added tungsten to the copper, you get the benefits of the copper, which is high or very good or excellent thermal conductivity and electrical conductivity. And also add still increase the melting temperature, then melting temperature will be higher. You know that copper is 1000 degrees Celsius melting temperature, but tungsten 3500 plus. Then you get the benefit of both. This one is excellent actually. This one is excellent. Copper tungsten is excellent material to be used as electrode, but it is definitely more expensive than copper material. Right. This is the steps. Initially, you positioning the two material, and then you apply bring electrode, and you apply little pressure for positioning, and then here you apply little pressure. Little pressure, not high pressure, little pressure for positioning, only positioning. Then force applied here, force applied from here, this is the force. Force applied from here to the end. Here we release the force. At this level, we release the force. Later, after finish, we release the force. So, force applied from here to here. Current started here. This is the current. Current started here. When we apply force and positioning, we apply current. We start current here until here. Then current, a big amount of current, very small time. As I told you, 0.2 second, fraction of second. You apply time very quick, very fast. Then you apply current, then weld immediately done. Very high resistance temperature, quickly increase, you get melt, you get weld done quickly in portion of second. This is the relief current. This is the relief current, a short period, very short period of current to ensure that weld done perfectly. And then you release the pressure, and then you get weld done, as you can see. This is the steps of the spot welding, resistance spot welding. Another resistance welding, we call it seam welding. Seam welding is a line. Seam welding is it is actually spot welding, seam, but here the electrode replaced by a rotating roller. Here we're rotating roller. So when you have a rotating roller, it could make, as you can see here, several spots. It depends on the current frequency. If you have low frequency, then you get one spot, and then you get one spot, and then you get one spot, then you get one spot with big interval, you get several spots. If you make frequency is higher, you get also several spots. We call it overlap spot with very short interval. With very short interval. If you make continuous current, if you make continuous, you get line. If you make continuous, you get line. It depends on the current frequency, flock frequency, high frequency, you get overlap spot. But if you get continuous, you get whatever we call line, which is seam welding. Then you get seam welding. It depends on what you need exactly. This whatever we call seam welding. It is exactly spot welding, but also the electrode replaced by the rotating roller. Right. Next, the resistance welding is another type of resistance welding. We call it the projection welding. Projection welding, actually, we form the work part here to be contact in very small area. We design this one. We form it to this is the electrode diameter. The weld will not done in electrode diameter, but will done exactly in exact location, as you can see here and here. This is why we call projection. So weld, even the electrode diameter, you see that even electrode diameter is bigger. Even electrode diameter is bigger, but current will pass through only here and here, because current would like to pass. How current pass through from up to down unless through this kind of projection area. So current pass through exactly certain location. Then here area here will be melted and will done exactly not here in a gap, but here exactly in a contact point, which is a projection area. So we call it as a projection welding process. It's similar to spot welding, but is a different is that weld nuggets will be very small, located exactly in certain position, not like the weld nuggets will be bigger and equal to the diameter or similar to the diameter of electrode in a contact area. This is a big difference between projection and spot welding. Next, we call it is flash pot welding. Flash pot welding here, we need to weld this kind of cylinder, two cylinder together. Then heat generated by resistance and arc. Initially resistance and then arc. Resistance will start initially in contact and get resistance, and then a separate pose and arc will be created. And when arc will be created, material will be heated up to enough temperature, and then you apply pressure. You apply pressure here. Well done, actually well done here in this zone. They call it is flash pot welding, and sometimes they call it arc welding also as well. Resistance welding, and some they call it resistance welding. They call it arc welding. They call it flash pot welding. This is a welding process. Another welding process, resistance arc welding process. Self-reading, some other welding process also not very commonly used but exists in industry, like cross wire welding, upset welding, precursions welding, high frequency resistance welding, high frequency induction welding. This kind of welding process is self-reading. It is located in page 584 in a welding process. So please just go through and read it. Same fundamental, I guess. So reading this one will not be really difficult. So this is kind of self-reading assignment for you. Next, we talk about the oxfoil gas welding. Oxfoil gas welding is a flame welding. So now we cover what we covered in this chapter. We cover the arc welding, consumable electrode and non-consumable electrode. Also, we discuss about the resistance, different type of resistance welding, spot welding, seam welding, and projection welding, and flash pot welding. And now we're going to talk about oxfoil gas welding. Oxfoil gas welding is a flame. We're going to create flame. This is a cylinder, gas cylinder. This is a torch, and we're going to create flame. And we're going to use a flame to heat a workpiece material to do the welding process, right? This is a torch actually. This is a torch. When you look to the torch, this is whatever we call mixing chamber. Mixing chamber. Mixing what? Mixing gas. So there are two types of gas. Oxygen. This is the oxygen. The blue color is the oxygen. The yellow color is a fuel gas. Fuel gas. You pump here and then both mix together. So here in the mixing chamber, we mix oxygen with the fuel gas together, and then we fire. We create a flame. We fire this one, you get a flame here. This flame being used to heat and melt and weld the material, weld the workpiece material. Right. Oxfoil gas welding. Commonly we use acetylene. Commonly we use acetylene. Acetylene is a common gas being used as a fuel gas, which is a C2H2. Acetylene is a common gas being used in welding. So chemical reaction happen like that because we mix oxygen with acetylene. Acetylene is a fuel gas. Oxygen, when react together, you get you get 2CO plus H2 plus heat. This is get 1/3 of the heat. And then again more reaction, 2CO, this one 2CO plus H2 plus 1.5 oxygen, another oxygen, get to CO2 and H2O and heat, you get 2/3 of the gas. And finally get the heat needed for welding. This is oxyacetylene gas. Acetylene is the most common and need added separate filler. So this is a torch. Can you see that in a photo? This is a torch actually. This is a flame. This is a filler. This is a filler. Filler must be added actually. A filler must be added separately as you can see here. Then filler must be deposited as you know, as we described earlier in the previous chapter. Then you get three type of flame you get in oxyacetylene gas. If oxygen and acetylene mixed at same ratio, this is a normal flame being used with the most majority of the material. If oxygen bigger than acetylene, we call oxidized flame. If acetylene bigger than oxygen, we call it carburizing flame. Oxidizing flame is being used for copper and base alloy because it provides thin protective layer of slag. This one providing thin protective layer of slag and being used with a copper and copper base alloys. Usually used copper and copper base alloys. If it is carburizing means acetylene bigger than oxygen, the percentage of acetylene bigger than oxygen, you get this one. You can see the flame, the shape of the flame actually different, temperature also different from case to case. This one will be used as a brazing and soldering, which is a liquid solid state welding because you get lower temperatures. The lowest temperature you obtain in this case when acetylene bigger than oxygen. We call it carburizing and being used in the soldering and the brazing because temperature is lower. Because the filler material usually used in a brazing have a lower melting temperature. So this one is suitable for for welding the liquid solid metal welding, which is the soldering and the brazing welding process. Right. There are not only acetylene but several types of gas being used. But as I told you, acetylene is the most common gas being used in welding. This is the acetylene. Right. More than acetylene, many other gases being used, as you can see here, MABP, hydrogen, propylene, propane, and natural gases. Several types of gas being used. This is the temperature being generated at the when flame is created. This is the temperature. This what we call is the heat of combustion. The word heat of combustion means the amount of heat released from the amount of heat released from combustion of what? Combustion of these gases, right? For example, if you talk about acetylene, when flame is created, when combustion happen in acetylene, it releases around 54.8 megajoule per cubic millimeter of acetylene. When burning 1 cubic meter, listen to me carefully, please. When burning 1 cubic meter of acetylene, it releases 54.8 megajoule. So this is the volume, 1 cubic meter volume of acetylene, only acetylene. I'm not talking about oxygen. Now, because this is the fuel heat, or heat released from the fuel burning or fuel combustion, then 1 cubic meter of acetylene release 54.8 megajoule. This one is, if you multiply the heat of combustion, megajoule per cubic millimeter, if you joule cubic millimeter or megajoule per cubic millimeter, this one, let me highlight this one. If you multiply this one, which is the heat of combustion, if you multiply by volume rate of fuel, what is a fuel? Fuel, for example, if you talk about fuel, for example, acetylene, volume rate of acetylene, which is cubic meter per second. Then you get joule per second. Then you get what? You get joule here. You get joule per second. Joule per second mean heat rate. Then again, heat of combustion, this one, which is joule per cubic millimeter, if you multiply by volume rate of fuel, because The fuel is delivered at certain rate, right? Volume rate of fuel, which is cubic meter per second. Cubic meter with goes the cubic meter, get joule per second. Joule per second, which is what? Which this is the heat rate. If you multiply by the volume of the fuel, which is a cubic meter, just volume of the fuel from beginning to the end. Volume of the fuel needed to do the weld from beginning to the end, then cubic millimeter goes and you get joule, which is heat. This is a two case. You can just get joule, which is the heat, or you get joule per second, which is the heat rate. If it is joule per second, which is the heat rate, you use this equation, RHW equal to F1, F2, RH. This is the RH. This is the RH here. This is the RH being used here in RH equal to UMAV. If you multiply not by volume rate, multiply by the volume of the fuel being used from beginning to the end. For example, half cubic meter is the volume of the fuel being used in all process. Then you get cubic meter goes, you get joule, which is the heat. You have to use heat equation. So be careful about that. This is the heat of combustion. Let's take an example and read it together and see how to deal with this example. Okay, let's read together an oxyacetylene welding process. Torch supply, this oxyacetylene torch. Supply, this is a two input here, two gas input here. This is oxygen and acetylene, as you can see. This is oxygen and acetylene. This is an oxyacetylene torch supply, 0.3 cubic meter acetylene. Let me highlight. Then be careful, 0.3 cubic millimeter acetylene per hour. Per hour. This is the volume rate. 0.3 cubic meter per hour of acetylene, and equal volume rate of oxygen. Equal volume rate of oxygen means that oxygen delivered also at 0.3 cubic meter per hour. It doesn't matter. This one not very important to me. What is important to me? Important to me is the acetylene volume rate. Fuel volume rate. What is important to me is the 0.3 cubic meter per hour of acetylene. This is it's important. For an oxyfoil gas welding, or here this is a oxyfoil gas welding operation, 4.5 millimeter thick steel. This is the one, 4.5 millimeter thick steel. Heat generated by combustion is transferred to the work surface. Heat generated as a source. Then heat generated as a source here. Here generated as a source, right? RH. Heat generated as a source equal to RH. RH is the heat generated here as a source, which is equal to heat of combustion. Heat of combustion is given. This is the heat of combustion. You multiply by 0.3 cubic meter per hour. You get heat rate generated at the source. This heat generated at the source transmitted to the work surface with the heat factor F1. Then F1 here is 20% given. Heat 1 F1 equal to 20%. It is given actually. This one F1 equal 20%. He told me like this. If 75%, then the heat transmitted to the surface. Now we talk about heat transmitted to the surface equal to RH multiplied by 0.2. If you get RH multiplied by 0.2, you get the heat transmitted to the surface. If 75% of the heat transmitted to the surface is concentrated in the circle area of the work surface that have 9 millimeter in diameter. So this one is 9 millimeter in diameter. The white color area is 9 millimeter diameter. Then in 9 millimeter diameter, 75% of the heat will be concentrated. The area here, 75% of the heat will be concentrated in this circle, which is 9 millimeter in diameter. 9 millimeter in diameter. Find the rate of heat liberated during combustion. Okay, this is the first one. RH. We need to get RH. Second, ratio of the heat transmitted to the work surface. Third one, average power density in the circle area. One by one, one by one. Rate of heat liberated during combustion. We have here heat of combustion. Heat of combustion, if you multiply by the 0.3, which is the volume rate, then you get heat liberated during combustion. Heat liberated during combustion, which is the RH. Heat rate or rate of heat, RH, rate of heat liberated or generated as a source, equal to the heat of combustion multiplied by the volume rate of the fuel. Then you get this one. Second, rate of heat transmitted to the work surface, you multiply by F1. This RH, if you multiply by F1, you get the heat rate transmitted, not used in the welding. Used in the welding, you have to multiply F1 and F2. I don't have F2. I don't need even. He didn't ask me. He asked me what is the heat rate transmitted only to the surface. How many percent will dissipated later in a workpiece? This is another story. I'm now going to obtain or going to calculate what is the heat rate transmitted to the surface. You multiply by 20%. And then finally, what is the power density in this circle, white color circle? What the power density equal to the power multiplied by the area. Let's go and see the solution one by one. First one, heat liberated at the source, meaning that 0.3 multiplied by the heat of combustion, then you get this one, joule per hour. You can change joule per second to get what? This is the joule per second, this is a watt, joule per second. It is actually, this value is a joule per hour. This 1 joule per hour, you can multiply by, you can divide, so you divide by 60, you get joule per second, which is watt. This is watt. What is the power generated or heat rate generated at the source? Second question, what is the heat transmitted to the surface? Only surface, not being used in a weld. RHW, which is the heat rate used in welding, F1, F2, RH. But I don't want that. I don't want to calculate RHW. Even he didn't give me F2, a melting factor. He just give me only F1. You multiply RH F1, you get the heat. This is the amount of heat rate. Be careful. This is the heat rate delivered to the surface. This is the heat rate delivered to the surface. Some of this heat will remain for welding. Some of this heat will dissipated in the workpiece. It depends on what? Depends on F2, which I don't know. So this is the heat rate or the power. This is the power or heat rate delivered to the surface. 75% of this one, 75% of this one concentrated in an area, white color area. 75%, let me write, 75%, 75% of this heat rate, this heat rate or this power, 75% of this power of this heat will be concentrated in 9 millimeter diameter. This is the area of 9 millimeter diameter. Then the power density equal to 75% of the heat rate or the power. This is the power concentrated in this circle divided by the area of the circle. You get the power density. This is the power density here in a white color area. Power density in a white color area. I hope you understand. Still, if you have any question, if you would like to ask me anytime, you are very welcome. We can just discuss in office hour time. Right. Finally, is whatever we call is a pressure gas welding. Pressure gas welding. A pressure gas welding is another technique in a gas welding. Here, while we are heating the two parts that we would like to weld in the weld zone. We're heating this one and we're heating this one. Whenever you get start melting, then you release this one and apply pressure. Then well done, liquid, well done in these areas. You call it as a pressure gas welding. So parts are heated until melt begin on the surface, and then you remove the torch and apply pressure to get the weld done. Right. Next, we're going to talk about the weld quality. Next, we're going to talk about the weld quality. Actually, time is finished. Then I have to stop here. And next time, inshallah, I'm going to talk about the weld quality. If you have any question, you are very welcome to ask me during the office hour. Office hour every Sunday, Tuesday, Thursday from 1:30 to 3. You are very welcome anytime. Okay, that's it today. Next time, I'm going to talk about the weld quality, inshallah. Thank you very much and see you next time. Assalamu alaikum jami'an.